So now we are continuing with the topic of hog, which is used to process for calculating the hog that for the feature extraction. Here we can see that how we would now have a basic idea of what the hog feature descriptor is basically, and it is a time to dwell into the core idea behind this article. And let's discuss about this step-by-step procedure of calculating the hog. So consider here one of the image of size 180 by 280. Let us take the detail look here. In this given image, we'll create given image. Now here in the first step, that process the data of 64 by 128 of that image. So here we can create the image data of 64 by 128. We need to pre-process the image and bring down the width to height ratio of 1 of 2. So image size could preferably be 64 by 128, and this is because we will be dividing the image into 8 by 8, 16 by 16 patches to extract the features. So having the specific size 64 by 128 will make the all our calculations pretty simple. So here our original image, and this is our resize image which represent the size of 64 by 128. Step 2, to calculate the gradient of the image, which is in the direction of the x and y. So here the gradient for every pixels in the image we are going to calculate, and that has a small changes in the x and y direction. So here some we consider or take some small patches from the images and calculate the gradient on that. So like hop features, we'll get here the pixels value for this patches. Let's say the generate the below images. We can see here that this is one of the image, and this we have extracted one patch of this images. Okay, and here that patch which represent the maximum patches or some we are trying to extract from the images, and that patch is nothing but the matrix which shown here is merely used as an example, and these are not an original pixel value for the given patches basically. So here we can have one of the patch with the matrix representation, and some highlighted pixel value we can have over here, that is 85. And now here we are going to determine the gradient in the x direction, and we need to subtract the value on the left from the pixel value, like from the 89 to 78, and from the 68 to from 68 to 56. So for the x direction you can have 89 minus 78, and for the y direction 68 minus 56. So for the x direction you'll get the 11 pixel size, and for the y direction you'll get the 8. So this process will give us the two new matrix, one storing the gradient in the x direction and the other storing the gradient in the y direction. So this is similar to using a Sobel kernel of size 1. So magnitude be higher when there is a sharp changes in the intensity such as around the some edges. So we have calculated the gradient in the both x and y direction separately. The same process is repeated for this all pixels in the images. And now for the third step, calculate the magnitude and orientation. Using the gradient, we calculate in this step. In the last step, we'll now determine the magnitude and the direction for the each pixel value. For this step, we'll be using the Pythagoras theorem for calculated values of the x direction and y direction. So here you know that we have calculated gx and gy basically, that is your 11 and 8, and we are using the Pythagoras theorem to calculate the total gradient magnitude. So in that case, square root of this g of x square plus y square, and total here we will get the value 13.6. So g of x and g of y image will be represented like this, and it's you can say it's a gradient magnitude which we have calculated, that would be look like this image. So orientation, where the next calculate the the direction for the same pixel, that is to be called as a orientation. And we know that we can write the tan for the angles like g by gx. This is a tan function represented with this g by gx. Hence the value of the angle would be tan that is this same equation will be represented with this, that angle is to be calculated and orientation come out to be a 36 when the we plug in the values. And so now for every pixel value we have a total gradient and the orientation, and we need to generate the histogram using this gradient and orientation. So here there is a method to create histogram using the gradient and orientation. So histogram is the plot that shows a frequency distribution of the set of continuous data, and we have a variable in the form of bins on the x-axis, frequency on the y-axis, and we are going to take the angle and the orientation on the x-axis and the frequency on the y-axis. So let's make a small modification to our method, and we will add the contribution of the pixel gradient to bins on the either side of the pixel gradient. Okay, so here we need to remember that higher contribution should be the bin value, which is closer to the orientation. So here we know that we have already calculated the magnitude, that is 13.6, and orientation angle that is 10, that is 36, and here that is represented with the bin. So magnitude and bin has been represented with for this given value. So here you can have a gradient magnitude, gradient direction that is represented for some pixel values, and we have extracted some feature vector of the size 9 from this grade magnitude and the direction. So next step is to calculate the histogram of the gradient in the 8 by 8 cell. This is called as 9 by 1. So histogram created in the Hawk feature description are not the generated for the whole image. Instead, the image is divided into the 8 by 8 cell, and the histogram oriented gradient is computed for the each cell. Here by doing so we get some features or the histogram for the smaller patches, which is in turn represents the whole images. We can certainly changes this values here from 8 by 8 to 16 by 16 or 13 by 32 by 30. So if we divide the image into the 8 by 8 cell and generate the histogram, we'll get the 9 by 1 matrix for the each cell. So this matrix generated using the method as we have discussed in the previous section. So once we have generated this hog for the 8 by 8 patches in the images, the next step is to normalize the histogram. Normalize next is a normalized gradient in the 16 by 16 cell. So before we understand how this is done, it's important to understand why this done in the first place. So although we already have a hawk feature created for 8 by 8 cells of the images, gradient of the image are sensitive to overall lightning. So this step basically normalize the gradient in the 16 by 16 cell, which is nothing but 36 by 1, and in these steps 18 by 8 cell with the 9 by 1. So calculating of histogram of gradient with 8 by 8 cell and normalize the gradient with the 16 by 16 cell. So this is the next step, means for the particular picture or some portions of image would be very bright as compared to the other portion. So we cannot completely eliminate this from the image, and we can reduce this lightning variation by normalize the gradient by taking the 16 by 16 blocks. Here is the example that can explain that 16 by 16 blocks are created. You can see here that 16 by 16 blocks are created with some gradient magnitude and directions and feature vectors of the size. So here we will combining 8 by 8 cells to create 16 by 6 block, and here as you know, as we know that 8 by cell has 9 by 1 matrix for the histogram, and have a 4 9 by 1 matrix and single 13 16 by 1 matrix. And to normalize this, we'll divide each of these values by square root of the sum of squares of values, and mathematically here it is represented, that is v is equal to a1 a2 to a36. We calculate the root of the sum square of this, that is square root of this a1 square a2 square to till a36 square and divide all the values in the vector v with this value, that is normalized vector is represented here, and the result would be the normalized vector size of 36 by 1. So features for the complete image here we have created, that is we final steps of generating hawk features for the image, we and actually so far we have already created the feature for 16 by 16 blocks of the image, and now we'll be combining all these to get the features for the final image. So here we can guess what would be the total number of features that we will have for the given image. So first need to find out how many or how many such 16 by 16 blocks would get for the single 64 by 128 images. So that we are going to find here, and total 3780 features we have extracted for the given image based on this 16 by 16 blocks with the 7 by 15 blocks of 16 by 16 image. So we'll now generate hop feature for the single image, verify if we get the same number of feature at the end. So gradient can be represented for that all images over here, and likewise we can extract the feature using the hop. Okay, thank you.